Okay, so we're going to take a look at Chapter 4, Section 1. Chapter 4 is all about electrons. We're going to take a look at what are electrons, where are they located, specifically like which orbitals we'll take a look at in Section 2. And in Section 3, we're going to do what's called electron configurations. You're going to tell me where do all of the electrons exist within each element, essentially. And it's not the easiest thing in the world. I mean, this stuff is not super, super easy, and it does require a lot of thinking and a lot of effort. So, the first thing I'm going to tell you, especially in chapter 4, is to read the textbook. So, the first place you should go, and if you're watching this video to follow along with the notes, please make sure you have your textbook opened up. I am on page, I guess this section starts on page 97 is where 4-1 starts. So I would open up to page 97 to at least kind of follow along with the notes. Then I would also take a look at, reading that outside of this as well. So once we're done with the notes, I would go through and actually do a full deep reading of this section, okay? Because it is not the easiest thing in the world. So I would take a look at it. Okay, so chapter 4, section 1 is mostly about waves. And the reason it's about waves is because electrons themselves can behave kind of like waves. So section 1 here is on wave particle duality and electron excitation. So visible light itself, visible light is a kind of electromagnetic, oops, okay. Don't know why it jumped all the way down. Okay, it's a form of electromagnetic radiation. Okay, so visible light is a form of electromagnetic radiation. A lot of times I just call this light. Okay, this is just light. Now, not all of it is visible light. That's what you usually think of when you think of light, is like the light you can see. So here's a chart showing all the different types of electromagnetic radiation. So one type right in the middle is visible light. That's this section here, that's visible light. But visible light only exists within a short range, okay? If the energy increases, I start coming over here to ultraviolet X-rays, and eventually my super high energy light is called gamma rays. I can't see any of this. Okay, we can use it like X-rays, we can use X-rays, we can use gamma rays, but I can't see any of this. Okay, on the flip side, as my energy decreases, as my wavelength gets longer, I've got infrared, microwaves, and eventually at the end here, I've got radio waves. These all have a really long wavelength. They've got a really short frequency, and I can't see them. So I can only see light within this specific area of the electromagnetic spectrum. Okay, that's my visible light. But all of this, all of these different types of electromagnetic radiation, they're all light, just not all of it is visible light. Okay, so they're all waves. Waves have a couple of important properties. The first property is the distance between two corresponding parts on adjacent waves. This is called the wavelength. So this tells me the wavelength, how long the wave is. And we use this symbol here. This is called lambda. Lambda, it's a Greek letter, and that symbol is what we use for wavelength. Okay, so I write lambda maybe like that. Maybe you can write it like that, whichever way you prefer to write it, but that's the Greek letter lambda. It represents wavelength. Wavelength is like the distance between like this peak and this peak. If I look at those two peaks and I find the distance between them, that's the wavelength. Okay, I can have a longer wave. Something like this has a longer wavelength, or I can have really short waves. Okay, something like this is a really short wavelength. Okay, but the wavelength tells you how far apart are those peaks or those troughs. Okay, moving on further, not only do I have wavelength, but I have another property of light called the frequency. The frequency is like the number of waves which pass a specific point. It's kind of like the opposite of wavelength in a way. So if you look at these two examples here, the top example has a long wavelength, but that means the frequency is low because I'm not getting as many of these waves at a time as I am here. Okay, I'm getting a lot of waves here, so the frequency is really high, but notice that the wavelength is shorter. Okay, so if my frequency of my wave increases, my wavelength decreases, and vice versa. Okay, so frequency just tells me how many peaks and troughs am I getting. Okay, if I have a lot of peaks, I'm going to have high frequency. If I have not many peaks, I'm going to have low frequency. So those are the two things we need to know. We need to know frequency and we need to know wavelength, and we need to know that they're kind of inverses of each other, right? As my frequency increases, my wavelength decreases, and vice versa. Okay. For electromagnetic radiation, the mathematical relationship between frequency and wavelength is written like this. C equals lambda times V. Remember, lambda is your wavelength, and V is your frequency. Okay, sometimes we call that velocity, like V for velocity, but that's like our frequency. What is the C? Well, the C is actually the speed of light. And the speed of light is the same for all light. So if you have an X-ray or you have visible light or you have a gamma ray, any of those are going to have the same speed of light. And that's constant. And that is equal to 3 times 10 to the 8 meters per second. Okay, so the speed of light is 3 times 10 to the 8 meters per second. That's a constant. It's always equal to that. So whenever you're doing calculations, always use 3 times 10 to the 8 for C. That's our speed. Okay, we can rearrange formulas, by the way, to solve for whatever it is that I'm looking for. So if my question asks me to find the frequency, then all I have to do is solve for V. And I can solve for V by dividing by lambda. Okay, so if I wanted to find my frequency, I would say V is equal to C divided by lambda. If I divide both sides by lambda. Okay, now I've got an equation for frequency. I can do the same thing if I wanted to find an equation for wavelength. If I wanted to find wavelength, I just say, well, lambda is equal to, again, I would divide both sides by V, C over V. Okay, so all I have to do is manipulate the equation and I can solve for anything. So in your homework, I might ask you a question to calculate the frequency. If you have to calculate the frequency, there you go. Okay, all you have to do is plug in your C, which is here, and whatever your wavelength is. I will give you the wavelength. Okay, plug those two in, you should be able to find the frequency. You should then be able to find the wavelength going the opposite direction. Okay, so just manipulating these equations. Okay, so that's all about light. Light is this wave, and it's got a frequency, and it's got wavelength, and it's got all these different properties. But in the early 1900s, there was a problem through what's called the photoelectric effect. You can read about this in the book. I highly advise you read about it. If it's still kind of confusing, I would look up more about the photoelectric effect. You can also come talk to me and I can explain it more. But with the photoelectric effect, we found out that light sometimes behaves like a particle, which is kind of interesting because typically waves and particles are two different things. So like this is a wave and this is a particle, and those two are not the same thing. If you think about like a beach wave is not the same thing as a particle. Those two things are different. Okay. But it turns out that light kind of behaves like both. It behaves like a wave and it behaves like a particle. And when it behaves like a particle, we call that a photon. When it behaves like a particle, we call it a photon. Einstein did a lot of work with this where he described what photons are. And specifically, the energy of these photons can be calculated using the following equation. So here's your second big equation. E equals, and remember E is energy, is equal to H times V. Now this V we've seen before. This is just the frequency. This E is my energy of my photon. And this H is completely new to you. You've never seen this before. This is called the Planck constant. Okay, now the Planck constant is another constant that has the same value no matter what. So when you're using this equation, H is going to be the same every time. And this H is equal to 6.626 times 10 to the negative 34. And this is measured in joules seconds. Okay, so J times S, that's joules seconds. And this is a constant. So every time you see H, it's always going to be this value here, 6.626 times 10 to the minus 34. Okay, so if you know your frequency, all you have to do is plug in your frequency, multiply it by this Planck constant, and that will give you the energy of the photon. So there are a couple of questions in your homework that might ask you to use that equation as well. Okay? Okay, here's the key idea. The biggest thing that I want you to take away from this section is dealing with electrons within the atom. And you're saying, well, Mr. Williams, we just spent the whole time talking about light. That has nothing to do with electrons. Well, it kind of does. Okay, here's how we're going to connect the two concepts. The first thing we need to know is that electrons like to be in the lowest energy levels possible. So if I have an atom and I've got like a nucleus, for example, so let's say this is my nucleus. Surrounding my nucleus, I have, and remember that in the nucleus are your protons and your neutrons. Your electrons exist outside the nucleus in specific energy levels. So here I've got two different energy levels. Electrons prefer to be, like this is an electron, for example. These are two electrons. They prefer to be as close to the nucleus as possible. So if there's room in this first energy level, the electrons would prefer to be there. They don't really want to be out here unless they're forced to. Okay, so they don't want to necessarily be out there unless they're forced to do so. Okay, so they mostly want to be inside. This is called the ground state. When electrons are as close to the middle as possible, that's the ground state. Now, sometimes an electron, and I don't know if I have a good color for this, which is kind of unfortunate. Okay, I can change it up here. Sometimes an electron is going to absorb a photon. So light is going to hit one of those electrons. And we know that light has specific energy by that formula above. Okay, so light has this energy equivalent to the Planck constant times its frequency. If that light has enough energy, then it's possible that this electron can kick up to the next highest level. Okay, so that electron absorbed some of the energy from the photon, and it jumped up to a new energy level. Okay, it did so by absorbing that photon. It absorbed the photon. Okay, so I say here, when electrons absorb exactly enough energy from photons, they move to a higher energy level. They were at a lower one, now they've moved up to a higher one. But the electron, like I said earlier, does not like to be in this higher energy level, so it's going to try to come back down. So this electron would love to jump back down to this lower energy level. But in order to do so, it has to give off energy. So this, in order for this to happen, in order for this electron to jump back to this smaller energy level, it's got to give off a photon. Okay, so that photon has to launch out of the atom. Now that photon can have a different color depending on how much energy, the electron had to lose to jump from the second energy level to the first energy level. Okay, depending on where the electron jumps from is going to determine what color of light is emitted. So here's an example of hydrogen. Okay, so these are electrons in a hydrogen atom. If the electron goes from the third energy level down to the second energy level, it has to give off energy. Jumping from third to second is not as much energy as, say, jumping from fourth to second, fifth to second, sixth to second. So you don't need as much energy to jump from third to second. So it gives off red color. Red color has the lowest frequency, it has the lowest energy, and so jumping from third to second, it gives off a red color. Jumping from fourth to second gives off slightly higher energy because there's more energy between fourth and second, and that energy, because it's higher energy, becomes green. When an electron jumps from fifth to second, it gives off blue. And when an electron jumps from sixth to second, it gives off purple, specifically for hydrogen, because that's the difference in the energy levels. So if we look at what's called an emission spectrum, and I don't have one on your paper, okay, but in class we're going to look at this. If you try to excite a hydrogen atom, you're going to see four different colors. You're going to see like red, Then you're going to see like green over here, and then you're going to see blue, and then you're going to see purple. Okay. If you excite the hydrogen atom, you're going to see a spectrum like this, but you never see colors in between. You never see any color between red and green because the electron is only allowed to jump from third to second, fourth to second, fifth to second, and sixth to second. The electron is not allowed to jump like 3.5 to second. That doesn't work. Okay, it can't jump like between energy levels. The electron can't exist between energy levels. It has to be 3, 4, 5, and 6. It can't be anywhere in between. Because it can only take those very specific amounts of energy, it can only give off very specific colors. So if I excite a hydrogen atom by, say, running electricity through it, I should see the color released by hydrogen break up into these very specific colors, okay, because these are where the electrons are jumping from to give off those colors. If this is tricky, I completely understand. Okay, if this is difficult and you're like, I don't quite understand what's going on, I get it. Take a look at the book, read the textbook, see what they say about it, then come ask me questions as you have them. In class, we're going to take a look at actually exciting the hydrogen atom and taking a look at what we can see. If we can see these colors or not, sometimes it's hard to see in class, but we'll look at some other atoms as well that are a little bit easier to see. Okay, the main idea, as an electron drops from a higher energy level to a lower energy level, it has to give off that energy. That energy can't just disappear. So when it does so, it sends out a photon, and that photon has a specific amount of energy, which is equal to the difference between these two levels. So if this is level 1 and level 2, and it requires a certain amount of energy to kick an electron up here, it has to give off that same amount of energy to come back. And when it comes back down, it sends off that energy in the form of a photon. And depending on how far the electron had to fall, that energy might be different. Okay, if it has to fall further, if it has to fall from a really high energy level, like 6, down to 2, it's going to give off a photon that has a lot of energy, and that high energy photon is usually going to be like a purple, okay, because purple has higher energy than red. Okay, do your best to take a look at the homework. The homework has has a few questions about using those equations that we introduced before. As you have questions, please come ask questions and get some help as we go. Okay, thanks so much, you guys.